This video addresses Hückel's rules to determine aromaticity. According to Hückel's rules, there are 4 criteria for a compound to be aromatic, and those are: it needs to be cyclic, planar, completely conjugated, and have 4n plus 2 pi electrons. And n can be 0, 1, 2, 3, and so on, so long as it's not a fraction. Now let's look at benzene. We know benzene is aromatic. Let's see how it stacks up using Hückel's rules. It is cyclic, it is planar. Remember, each of these atoms in benzene are sp2 hybridized, and it is completely conjugated. Remember that each of these atoms has p orbitals, and so all the electrons are delocalized around this ring. Now, does it have 4n plus 2 pi electrons? Well, we can count that. It's got 3 pi bonds, and each pi bond has 2 electrons each, so it has 6 pi electrons. If you want to do the math, you can say 4n plus 2, is it equal to 6, and calculate n from there. And so n is 6 minus 2 divided by 4, so 4 by 4, which is 1. And so that's a whole number and not a fraction. And so that means that we fulfilled our 4n plus 2 pi electrons. You don't always have to do the math. You can just always look at this and say, well, if n were 1, you would get 6 pi electrons, and it does have 6 pi electrons. So to recap, Hückel's rules say that the molecule has to be cyclic, planar, and completely conjugated. If it's aromatic, it needs to follow those 3 Hückel's rules and have 4n plus 2 pi electrons. If it's anti-aromatic, it's going to follow all those 3 Hückel's rules, but it will have 4n pi electrons. Both aromatic and anti-aromatic compounds were discovered to be unusually stable if it was aromatic, and unusually unstable if it was anti-aromatic. The last category is non-aromatic compounds, and these break at least one of Hückel's rules. That is, they're either not cyclic, planar, completely conjugated, or more than one of those rules. And they're neither aromatic nor anti-aromatic. Now let's look at each of these rules. A molecule must be cyclic so that it can have overlapping p orbitals. It must be planar so that those overlapping p orbitals can have delocalization of electrons. So for instance, if this were a planar molecule and it is completely conjugated, then in that case we can see that the electrons would be delocalized all over the ring. Likewise, in benzene, the electrons are delocalized all over the ring because it's cyclic, planar, and completely conjugated. Now, if this 8-membered carbon ring twisted into a tub shape and was no longer planar, now you have p orbitals that are not aligned. So you've got these p orbitals in that pi bond that are vertical, and these p orbitals are now horizontal, which means that the electrons cannot flow through this entire system, and the electrons are no longer delocalized, and that means that it's not planar and not completely conjugated. Now, what is the significance of this? When we talked about stability, we said that aromatic compounds were the most stable, they were unusually stable, and anti-aromatic compounds were unusually unstable. Now, if we look at benzene, it follows all Hückel's rules. So it is cyclic, planar, it is completely conjugated, and it has 6 pi electrons, which follows the 4n plus 2 pi electrons rule. So this is okay. Now let's look at this compound, and here we've got 8 pi electrons, and that follows the 4n pi electron rule. And so, if this molecule has 4n pi electrons, it is cyclic, planar, and completely conjugated. That would mean that it is anti-aromatic. But if it was anti-aromatic, that means it's unusually unstable. And if the molecule has a chance, it will try and do something to break the anti-aromaticity and become non-aromatic, because then it would be more stable. And so in this case, what this molecule does is it bends out of shape into a tub, and because it does that, it's no longer planar, it's no longer completely conjugated, and so it's non-aromatic. Experimentally, we can actually determine this using NMR. You know that aromatic protons are more downfield than alkene protons, and aromatic protons are in the 6.5 to 8.5 ppm range. For benzene, this proton appears at 7.3 ppm, which is the correct range for aromatic protons. Alkenes, however, are slightly more upfield, and they are in the 4.5 to 6.5 range, and this proton is actually in that range. It's 5.3 ppm, showing that it's not an aromatic proton. The third rule requires that the molecule be completely conjugated. That is, it needs a p orbital on every atom in the aromatic ring. So while this diene is conjugated, this system is not fully conjugated. So it's not completely conjugated because you've got an sp3 carbon here, sp3 carbon here, and they don't have p orbitals. Likewise, in this 7-membered ring, this is an sp3 carbon, and so this molecule is not completely conjugated, and both of these are non-aromatic. And finally, once those three rules are fulfilled, you have to decide whether it's aromatic or anti-aromatic. Aromatic compounds will have 4n plus 2 pi electrons. Anti-aromatic compounds will have 4n pi electrons. So looking at these two molecules, count the number of pi electrons and determine if it's aromatic or anti-aromatic. So if we look at cyclobutadiene, we've got 4 pi electrons, and that means that it's anti-aromatic. It also fulfills all the other three criteria. Likewise, in naphthalene, it fulfills the cyclic planar completely conjugated criteria, and it's got 5 pi bonds, so it's got 10 pi electrons, which follows the 4n plus 2 rule, where n is 2, so 4 2s are 8 plus 2, so that would give you 10, and so this is aromatic. Now pause the video and predict whether these compounds are aromatic, anti-aromatic, or non-aromatic before moving forward. Assume all the compounds are planar. Now in this case, this is not cyclic, so it's definitely non-aromatic. If we look at the second compound, it's cyclic. It is not completely conjugated though, because it's got this sp3 carbon and this sp3 carbon. So again, it is non-aromatic. Okay, now if you were to consider these parts of the molecule, so this part is a benzene ring, this particular ring is aromatic, but overall the molecule is not aromatic. Now let's look at this 7-membered ring. This is called the tropylium cation, and it's got these 3 pi bonds, and it's got a carbocation here. Remember that carbocations are sp2 hybridized, which means that it has a p orbital here. So now, is it cyclic? Yes. Planar? We're assuming that they're all planar. It is completely conjugated because you've got p orbitals in all of these, including the carbocation carbon. And finally, how many pi electrons does it have? It's got 3 pi bonds, so it's got 6 pi electrons, which means that this is aromatic. Now let's look at this molecule. It's called thiophene. Remember that sulfur has 2 lone pairs, and if we were to assume that sulfur was sp3 hybridized, in that case it is not completely conjugated. However, remember that aromatic compounds are unusually stable. So if a molecule can become aromatic, it will try to do so. If a molecule is already anti-aromatic and it can become non-aromatic, it will try to do so. So it's always trying to go to the most stable possible form. And so in this case, if you were to draw resonance forms, you would see that sulfur is actually sp2 hybridized, so one of these lone pairs is going to be in a p orbital. And so that means that you've got complete conjugation, so completely conjugated, cyclic, planar, and if we were to count the number of pi electrons, we've got 1 pi bond here, 1 pi bond here, and one of these is in a p orbital. And so that leaves us with 6 pi electrons. and so it is aromatic. Now let's look at the next compound. Again, in this compound, remember this part is not cyclic, so overall the molecule is non-aromatic. The benzene, of course, is aromatic. So this particular system is aromatic, but overall the molecule is non-aromatic. Now let's look at this molecule. It's called indole, and just like in thiophene, remember that this nitrogen has that lone pair there. So if we were to look at this entire system, it is definitely cyclic. It's planar. Is it completely conjugated? Well, that depends on the hybridization of this nitrogen. So if this nitrogen were sp3, then it's not completely conjugated. If this nitrogen were sp2, it is completely conjugated. If we would assume that this nitrogen were sp2, let's count the number of pi electrons. We would have 1, 2, 3, and 4 pi bonds, and then we would have one lone pair that adds in, and so that would give us 10 pi electrons, which follows the 4n plus 2 rule. And remember that if a molecule can be aromatic, it will, because that would make it extremely stable, and so this molecule is aromatic. And just like with thiophene, for this molecule, you can draw a resonance form using this nitrogen lone pair to confirm that it's got sp2 hybridization.